And our next speaker is Antoni, from Flatiron CCA, who's going to tell us about hydrogen-rich gap transients in optical and infrared.
Everyone hear me? Great. Okay, hello, I'm Antoni. I am a postdoc at CCA, and first I just want to thank the coordinators for inviting me. I'm really excited to be here. I'm actually not an observer, so I've never been to anything like this before, and it's been like the opposite of the Wizard of Oz, where, you know, Dorothy sees behind the curtain, it's just like a regular dude. I'm seeing behind the curtain, and I'm just like, wow. Okay, so today I'm going to be talking about these hydrogen-rich gap transients. And by the gap that I'm referring to here is this gap that used to exist between classical novae, this has a little bit of a delay, and core collapse supernovae up here. But you can see, thanks to PTF, CTF, all of these wonderful things, this area is starting to be very filled in. And so what I'm going to talk about specifically today are these luminous red novae, which, is that better? No, okay, it's just this low. These luminous red novae, which is these sort of green angled swath here, the intermediate luminosity red transient, which is this red kind of smaller box, and then also something that is just theoretically sort of predicted may be observed are these failed supernovae, specifically from red and yellow supergiants, that are kind of predicted to live in this space here. And I should say, I shouldn't assume all of you have seen this kind of plot before. There's some junior folks here, and this is just this phase space of peak luminosity versus duration. Okay, so let's just dive in. So the luminous red novae. So these transients are characterized by their double peak optical light curves, where they have this initial blue peak that lasts maybe about a month, followed by this redder, longer peak that's kind of like a plateau lasting 50 to 200 days. And this sort of evolution from blue to red continues to the infrared because these, like all of the things I'm going to be talking about today, actually self-obscure with dust. So you're ejecting some hydrogen with a low amount of energy, and this material just naturally cools and so starts forming molecules in dust. And so you can see that in the infrared, so at 3.6 and 4.5 microns, this luminous red nova is still bright for many years. Okay, and so sort of spectroscopically, what is characteristic of these events is this oxygen-rich environment. And so after the second peak, as you're declining from the plateau, you start forming these oxygen-rich molecules. And you can see here, Nadia Blagnerovada is comparing this luminous red nova in black here to just the spectrum of an M-type star. And you can see these very deep, strong absorption features from these molecules. And then Viraj, of course, very recently did some very nice work with JWST, following up with these luminous red novae at 1,000 or more days, and finds evidence for these molecular species, also water vapor and silicate dust. So we know these are, this is sort of an oxygen-rich environment. Okay, now, and I just wanted to plug, Viraj showed us yesterday in his flash talk, the fact that these are very big dust producers. And he found with this JWST study that they probably contribute as much as 25% of the amount that core collapse supernovae contribute to the cosmic dust budget. And so these can be very important dust producers, just very generically. Okay, and right. So I haven't told you yet, but maybe many of you know that these red novae, these luminous red novae, are associated with stellar mergers. And the very clear evidence for this happened in 2008 with the system V1309 SCO, where the luminous red nova you can see happen in 2008, but the system had been observed with OGLE since about 2001. And so what they found was this over-contact binary on about a 1.5 day orbit. And this orbit sort of monotonically decayed in period, leading up to this luminous red nova, which is interpreted as a merger of this system. And indeed, there's no periodic signal in this system after that, so this is really believed to be a merger. Now, this is a very low mass system, and this was a contact binary. And so in this case, you already had one of the stars kind of contributing material to this sort of shared Roche potential early on the main sequence. This led to a merger. But you can also have binaries that are detached on the main sequence. So here you have two main sequence stars, and they don't start interacting until the more massive star finishes core hydrogen burning, crosses the Hertzsprung gap, the envelope expands, starts overfilling its Roche load, and this can lead to this runaway mass transfer, leading to this common envelope event. And now in this case, you can have two outcomes. In one case, you deposit enough orbital energy in the envelope to eject this material, and then you can have a surviving binary on a dramatically tighter orbit. Or you can maybe not have enough orbital energy, and these two things merge, but you're still gonna, eject some material that's gonna give you the transient signal and this dust at late times, because the energy that tightened this binary had to go somewhere. Okay, and so I actually, even though these are low energy things, I come at this from a massive star theorist point of view, where I want to know where the stellar mass black holes that come from massive stars are coming from and what are their properties. And so what's really exciting to me is that all of these luminous red novae are probing these very poorly understood phases in isolated binary evolution that are critical for understanding how you get the compact object binaries that are going to merge within a Hubble time and, of course, become gravitational ray sources. Okay, now sort of related to this, Roche slope overflow, the beginning of this common envelope and dynamical end spiral is that a lot of these luminous red novae, like with the 13909 STO, you see this brightening for years before the actual transient. And so, of course, this is interpreted as the onset of mass transfer or the beginning kind of slow part before you do the dynamical end spiral. And one sort of corollary to this, or I guess a result, is that because of this mass transfer early on, where you have material just sort of getting out of this potential of this shared binary, you can end up actually having significant amount of material in the circumbinary environment just before the luminous red nova. And so this is a movie from Morgan and McLeod, and based on these simulations and looking at different binary scenarios, what he finds is that actually there should be a population of luminous red novae from low mass stars that do this on the red giant branch. So this would be the donor star is low mass, it expands, it goes up the red giant branch, you go to this runaway mass transfer. So for these systems, the extinction should be quite high. So this is the local extinction. And so the actual luminous red nova could be completely missed in the optical. And so, of course, these are probably, this is a good sort of candidate system to be one of these sprites. So these especially red intermediate luminosity transient events. I literally cannot remember that without reading it. I don't know if Monsif can. And so I think the formal definition of the sprites is these things where there really is no optical signal to deep limits. But then there's also other things that Jake found in his PhD thesis where you have a very bright signal and maybe sometimes just like a shorter optical signal or dimmer than you would otherwise expect. So infrared is where it's at for a lot of these systems. Okay, so moving on to the intermediate luminosity red transients. So these are characterized by these single peak light curves that decline linearly from peak. And like the luminous red novae, you see this sort of blue to red evolution. These also produce a lot of dust. And so you can see that here's the 3.6 and 4.5 microns. For hundreds of days, you're still bright. And these are actually still blooming bright many years later, all of these ILRTs that we have observed. Okay, and so one of the ways that, because these two different types of transients, like if you look at ZTF, so if you look at Viraj's nice sample of both the luminous red novae and the ILRTs, the light curves don't look like these well-sampled ones that I've shown you. A lot of them, it's just like a line where you go, oh, this is brighter than it used to be. And so a big way of characterizing and identifying these ILRTs is because of these narrow H alpha and especially this forbidden calcium 2 line. And so typical just expansion velocities is like 600 to 1,000 kilometers a second, which is also similar for the luminous red novae. Okay, so when this class of transients first was coming around, and sort of since then, there's been this debate of whether these are LBV-like giant eruptions, so non-terminal mass ejections from very massive stars that are, 50, 60 solar masses, or low energy supernovae, that is sort of the, low energy explosions coming from the lowest mass of massive stars. And so some of the considerations that are helping to sort of end this debate is the fact that the spectra of these events have no wide lines or P Cygni features, which you would see in these LBV giant eruptions. And then also for 3 of these systems, the progenitor has been detected in the mid-IR. And I should say that the progenitor is not detectable in the optical or near IR. And so these progenitors are consistent with these very dust-enshrouded intermediate mass stars that are at the very bottom end of the red supergiant branch. And so this is very consistent with these ILRTs being electron capture supernovae of super AGB stars. Now, this is a very important population because it's probing a very critical and uncertain region in single stellar astrophysics. And that is trying to understand what is the sort of transition point between the low mass stars that die without an explosion and leave behind a white dwarf versus the lowest mass stars that can actually have an explosion and leave behind a neutron star at the end of their lives. And so, of course, see Kostov's very nice paper and thesis work really trying to, from the top down, find the lowest luminosity type 2Ps and try to understand observationally, what this cutoff mass is. And I should say from a theorist standpoint with stellar evolution codes, these super AGB stars are extremely difficult to model, not only because the envelopes are doing such huge pulsations that your code just crashes with hydro errors, but the nuclear physics is very complicated and you'll have different outcomes depending on how big of a nuclear network you do and everything. And so in my opinion, the way to get after this is really through observations and looking at, what are the rates of these things that we find compared to the IMF, and is that consistent with, let's say, a 10 solar mass cutoff for the lowest energy, the lowest mass star that can explode. Okay. All right, and so the sort of last little, I don't like to say nail in the coffin, the last puzzle piece maybe in our little puzzle is this. So Sam has done these very nice JWST observations and found this, PA feature in the spectrum, which is very consistent with carbon-rich dust. And so these super AGB stars, we expect, because they've had 2 or 3 dredge-ups, to have winds and environments that are very carbon rich. And so this kind of just really, to me, really drives home the idea that these are probably electron capture supernovae of super AGB stars, and these really aren't giant eruptions. Okay, all right. So the last topic is failed supernovae. And I'm playing with fire a little bit because I'm saving the most controversial topic for the end. And I specifically saved time for discussion. Okay, so this is more just theoretically predicted, though there's 2 candidates that I'll show you. And so I'm just going to say 2 simple things. And one is that in an uncertain fraction of core collapse deaths, the supernova mechanism actually fails. And this mechanism, specifically, I'm talking about this neutrino-driven turbulence-aided driving mechanism that would give you a canonical supernova, like a type 2P if the star is a red supergiant. And so basically what happens in this case, if the supernova fails, then the inner parts of the star collapse to form a black hole, and you're left with just the question of what happens to this hydrogen envelope as it's trying to fall in and accrete. And what I'll tell you is that for red and yellow supergiant progenitors, for a couple of reasons that I don't have time to explain in detail, that you actually still get a 10 to the 46 to 10 to the 49 explosion of this envelope, and therefore you should have an observable transient. Okay, and so just sort of a rough idea of what this kind of explosion would look like. Here's just instantaneous energy deposition into the envelopes of some red supergiants and some partially stripped yellow supergiants. And basically what you get is a two-peak, double-peaked light curve. This is zoomed in at the peak. This is the full light curve on the right. So you get something like a type 2P, but scaled down in energy, meaning that the overall event is dimmer, but because everything is expanding more slowly, the transient is much longer. And you can see the red supergiants, what would be a 100-day plateau in a type 2P supernova is now extended to 200 or 300 days. Okay, and so if I take just a set of red supergiants at the ends of their lives and partially stripped yellow supergiants at the ends of their lives, and I estimate what's the range of explosion energies you would have for those particular progenitors, given these couple of mechanisms for failed supernovae, you would have these ranges of luminosity on the plateau versus duration of the plateau for each of these progenitors. These are not light curves. This is the range of combinations of plateau luminosity and time you can have for the range of explosion energies that make sense for that progenitor, if that makes sense. Okay, and so just the takeaway from here is just that if you look at, so the red supergiant failed supernovae fall over here, the stripped envelope yellow supergiants fall here, and then I've added these filled points are 3 of the extragalactic luminous red novae with yellow supergiant or blue supergiant progenitors. And then these open points are the 3 ILRTs that we have progenitor detections for. And so this is just to kind of highlight that if you're looking for these other 2 events that I talked about, you should also find the failed supernovae, which is kind of fortunate and lucky. Okay. Okay, so there's 2 candidate failed supernova events that are still hotly debated. So the first one was announced in 2015, and this was found as part of Chris Kachanik's survey, where they basically for the last 15 years have been looking at about 1 million red supergiants, just waiting for them to disappear in failed supernovae. When they started the survey, they didn't know you should actually have a transient, but they found one anyway. And so basically you have this star that was marching along doing its supergiant thing, and then it brightened by a factor of 10 in the optical before dimming by 5 magnitudes in the optical. And you can see there's just this sort of infrared tail to late times that is persisting today. And if you look at the bolometric luminosity of the remnant today, and this is including JWST spectra, so we've got a very well sampled SED to be able to estimate the bolometric luminosity. I said that for you, Sam. That the remnant is about 10 to 15% of the luminosity of the progenitor before this event. Okay. Now, the more recent candidate that many of us in this room have worked on was found by Keisha Day in their searches for these other kind of low energy transients and NEOISE data. And so what they found was this, this star, which is consistent with a yellow supergiant progenitor, sort of just going along doing normal yellow supergiant stuff, typical yellow supergiant variability. And then you have this brightening by about 50% in the mid-infrared, and with a corresponding dimming in the optical. And then similarly, like the last event, you basically are non-detected in the optical, and you have a sort of power law fall off in the infrared. And I should say, just like the other 2, these are self-obscuring by dust, because again, you've ejected a bunch of hydrogen at low energies, you form molecules in dust, and you self-obscure. Okay. And this power law fall off is consistent with accretion of fallback material onto the nascent black hole. Okay, but again, there's disagreement here. Some people think these could be stellar mergers or some other kind of just stellar eruption or something, and that this really isn't the disappearance of the star. So we'll see how that works itself out in the literature. Okay, so just as a little mini summary of these 3 different types of transients that I've been talking about. The luminous red novae are, of course, we think are stellar mergers. And these are important because they're probing this very uncertain isolated binary evolution channel leading to these gravitational wave sources. The intermediate luminosity red transients, which we think are electron capture supernovae, of course, are important because they're probing the lowest energy massive stars that can leave behind a neutron star. And then these failed supernovae are these iron core collapse events without a canonical supernova. And these are probing the bursts of stellar mass black holes in a way that we just can't do with successful supernovae. And the reason that I say that is because when we see a successful supernova, we really don't know if it has left behind a neutron star or black hole. And so if we can understand what the observational signatures of stellar mass black hole looks like, we can start to do the black hole accounting in another way. Okay, and so the only thing you need to remember from this talk is all three of these things are very dusty. And this is a great time to be thinking about these dusty transients because, of course, now we have winter. And so you may have noticed almost everything that I showed you was optical photometry. And so if you want to understand what these things are going to look like with Roman, you really want to see these transients in an infrared time domain survey. And so that's what winter is giving us. And so this is just a very interesting object that Viraj has been following. And so this may look familiar from those luminous red novae, is that you're seeing this slow brightening and they're just following this luminous red nova. And it's now past the peak and they're continuing to follow. And so I'm excited to see where this goes. Okay, and so I'm just going to end. That's my discussion question, but I just want to end with this nice ILRT light curves from Sam and this JWST data from Viraj, because yes, I'm going to say it, the future is bright in the infrared, and I'll take any questions.
Over there. Yeah.
Oh.
First.
Oh. I'm sorry. That was an exciting talk. I'm really excited about infrared transients. I'm concern trolling. You know, Roman is coming. And how is Roman going to find these things? There's no real way of finding transients like this with Roman, as far as I know, right?
I see. Okay, yes. Well, I'll let Jake
I guess
take it.
It's a more
and I should really emphasize I'm the dumb theorist here, so I kind of fooled you by showing mostly observations. But actually, I mean, my discussion question is like, so we have winter, we have Rubin. How do we use Roman to add to this data set? Yes.
I guess, let me be blunt. I think there should be some kind of nearby galaxy transient survey with Roman. Otherwise, we won't be seeing these things with Roman. That's what I think.
Okay, fair.
Okay, next question. But I think she was first. Then we can go to.
Sorry about that. Okay. Are you sure?
Down there.
Thank you, Andrea. So while we have you here as the theorist, what are some physical, maybe related to the dynamics of these explosions, mergers, failed supernovae, etc., that you think would be most valuable for you to get from us as observers with future events? And what are we not providing that then continues to make us say, this was a merger, this was a failed supernova? What more would you like physically? We can give you velocities, we can give you more of the spectrum. What would you need?
I mean, this is up to nature. So, I mean, I think the real telltale difference between, let's say, a failed supernovae and like an intermediate luminosity transient is, you know, and with the M31 event, this thing was so close. So we had everything. And so you kind of need to know what was the star doing before the event? What is the nature of the progenitor? Enough data, both on the transient itself, but also in the follow-up to get a really good SCD so you know what the bolometric luminosity is doing. And I mean, that's what we have with M31. And I mean, honestly, the data is better than the models at this point for the failed supernovae. So I think I just need like students to help me. But I mean, you know, an LSST, I think for, you know, folks 10 years from now, we're going to have a lot of data on these progenitor stars. And so I really think this is, you know, we'll have this legacy data going forward, which will really help. But really it's just, does nature give us a transient where we happen to have serendipitous coverage of the progenitor? But the follow-up I think is really critical. And especially with these infrared things, because eventually, you know, 5-10 years from now, these failed supernovae should start to not look like black hole accretion if there is in fact a surviving star.
Okay, perfect. Thank you.
A very, very, very quick question.
For the non-controversial part, the intermediate luminous red transients, which I always say backwards,
Yes.
and its interpretation like LBVs. LBVs should be changing color with the temperature, and they should be very bright because they're close by. Why are you saying only the spectra can disentangle them from?
No, I think there's
yeah.
many arguments for the progenitors are not bright enough to be LBV progenitors. And you also don't see the fast outflows that you see. And the progenitors are these dusty AGB stars. Oh, and I didn't show you, but there is also in these light curves, there's maybe evidence for a radioactive tail that with a very little amount of nickel produced. And so this would also be, yeah. So, I mean, I'm not in the LBV camp. I'm just trying to present both sides, but I think there's a lot of evidence. And also the fact that this is a carbon-rich environment instead of oxygen-rich.
Okay, let's thank Andre again.